Students, in this video I am going to establish the convergence of Gauss-Jacoby method. So first of all, what is the convergence criteria? So for that, since in the last few lectures we have already discussed about the how to solve this system of equations like ax is equals to b. We have taken some direct methods like Gauss elimination, Gauss-Jordan method. Then we have taken iterative methods like Gauss-Jacoby and Gauss-Seidel method. We have already taken LU decomposition methods like Kraut, Doolittle and Cholesky. So herein we are discussing about the convergence criteria for iterative methods. So matrix form of Gauss-Jacoby and Gauss-Seidel method we have already discussed it. So suppose we have the system Ax is equal to B, then we can rewrite this system in this form: x is equal to Tx plus C, and in iterative form this can be rewritten as this: x k plus 1th iteration is equal to T at x at kth iteration plus C, where x is nothing but the vector of unknowns at kth iteration, C is a fixed vector, T is a matrix, and here K is nothing but 0, 1, 2 and 3. We have already discussed this formula for Jacobi method. Suppose Ax is equal to B, then in what is A? A is nothing but D, L and U, diagonal matrix, lower triangular and upper triangular. If you combine these two, then we will have A. This is shown herein. A is nothing but the diagonal entries plus lower triangular entries plus upper triangular entries. So this is D plus L plus U. Now here if you take D in the left hand side and L plus U in the right hand side, so we have dx is equal to minus L plus ux plus b, because we are trying to write down this in this form or in this form, and we can rewrite this in this form in the various forms. This is one of them. We have taken diagonal entries in the left hand side, however the lower and upper triangular entries they will be taken in the right hand side. Now this is if D inverse exists, that means all the diagonal entries are non-zero. Then if you pre-multiply by D inverse, then we will have x is equal to minus D inverse L plus ux plus D inverse b in iterate. So now we are having this form. Initially we have this, we have rewritten this in this form, and this is nothing but this type of form where T is nothing but minus D inverse L plus u and C is nothing but D inverse b. Fine. Now in iterative form, this is nothing but xk plus 1 is equal to minus D inverse L plus u xk plus D inverse b, where k is 0, 1, 2. So what is T? T is this. This is T. This is your C. And this is basically the Jacobi method. We have already discussed this thing in our previous class. Then we have this Gauss-Seidel method. Now Ax equal to b is, again we will take this, and now we will take the upper triangular, this diagonal plus lower triangular in the left hand side, and we will take this upper one in the right hand side. So this is nothing but D plus Lx is equal to minus ux plus b. Now pre-multiply by D plus L inverse, so x is equal to minus D plus L inverse ux plus D plus L inverse b, and in iterative form this is xk plus 1 is equal to minus D plus L inverse uxk plus D plus L inverse b. So this is your C now, and this is your T. So T is minus D plus L inverse u and C is equal to D plus L inverse b. So this is your Gauss-Seidel method. Fine. So depending upon our choice of T and C, we have different methods. Here we have taken only two methods, Gauss-Jacoby and Gauss-Seidel method. Now we will discuss the convergence analysis of these two methods. What are the conditions for which these methods will converge? So suppose we have Ax equal to b, so convergence analysis of iterative methods. So let Ax is equal to B be the given system which can be written in the form of x is equal to Tx plus C. This is the exact form. So this is equation number 1, which is satisfied by true solution x. Now using any iterative strategy, 1 can be written as xk plus 1 is equal to txk plus 1. We are rewriting this in iterative form as this. This is equation number 2. Now this is the exact form. This is the iterative form. When you take the difference, then you will have the error. So just take the component wise. That means subtract left hand side from left hand side, subtract right hand side from right hand side. So xk plus 1 minus x is equal to t. You can take t common, xk minus x, and c is cancelled out with this c. Now this is nothing but the error in the k plus 1th iteration, and this will give you the error in the kth iteration. Hence, in terms of error, or error equation will be epsilon k plus 1 is equals to t epsilon k, where epsilon k plus 1 is nothing but this xk minus this xk plus 1 minus x is epsilon k plus 1, and this epsilon k is nothing but xk minus x is equal to epsilon k, where k varies from 0 1 2. Okay, so we obtain what? If you just rewrite this k plus 1 as k, then you have to rewrite k as k minus 1. That means we are basically decreasing the indices by 1. So here just decrease the index by 1, so we get k. Just decrease the index herein by 1, so we get k minus 1. Similarly, we are having here epsilon k minus 1. So again you can, from this equation you can find out epsilon k minus 1. So k minus 1, if k minus 1 will be here, so here will be k minus 2. Just substitute this value of epsilon k minus 1 herein. So we get t into epsilon k minus 2. Again you can find out the value of epsilon k minus 2, substitute it here, and so on. So ultimately we are increasing the powers of t and decreasing the iteration number of epsilon. So slowly you will see that after k number of times we get t raised to the power k epsilon naught. So this is epsilon k is equal to t raised to the power k epsilon naught, where k is 0 1 2 and 3. Okay, so this is the general formula. Now to establish the standard convergence criteria for Gauss, Jacobi and Gauss-Seidel, we need certain theorems, some standard results. So basically we are writing these results herein. Some results. First number, let A be a square matrix, then limit A raised to the power m will be 0 if norm of A is less than 1, or if and only if the spectral norm is less than 1. That means the meaning is that means the largest eigenvalue will be less than 1. So if largest eigenvalue will be less than 1, then obviously all the eigenvalues in magnitude will be less than 1. Spectral norm means the largest eigenvalue will be less than 1 in magnitude. So that means all the eigenvalues in magnitude, they should also be less than 1. Fine. So conclusion is that if limit A raised to the power m is 0, then the largest eigenvalue or all the eigenvalues in magnitude of this matrix A should be less than 1. Fine. Second, the infinite series I means identity matrix plus A square and so on converges if and only if limit m tending to infinite am is equal to 0. So this series converges if this holds, and if this holds, then from the previous theorem we can say that all the eigenvalues in magnitude, they should be less than 1. Fine. Now since this holds, the series converges to I minus A inverse, like binomial expansion, I minus A inverse. Okay. Now the theorem number 3. No eigenvalue of matrix A exceeds the norm of the matrix. No eigenvalue of a matrix A exceeds the norm of a matrix. That means norm of A is always greater than or equal to the largest eigenvalue, row A. Fine. Now we will use this theorem for the general one. Then we will establish for the Jacobi and Gauss-Seidel. But for the general point of view, theorem number 4, the iteration method xk plus 1 is equal to txk plus c for the solution of ax is equal to b converges to the exact solution for any initial vector if norm of t is less than 1. So we will establish this result here. Proof. So let us take x naught is equal to 0. Initially we have selected that xk is 0. 0 means 0 0 0. x1 is 0, x2 is 0, x3 is 0, because this is the vector of unknowns. So at initial stage we have taken all these unknowns as 0 0 0. So when we have substituted it here, then xk plus 1, that means for the next iteration this will become x1 क्योंकि k की वैल्यू 0 रख दी होगी. So x1 will be nothing but tx naught plus c, but x naught is taken as 0, so ultimately this will become 0, so we have only c, so x1 will be c. Again substitute this value herein by taking k is equal to 1, so we will get x2 is equal to tx1 plus c, that means this quantity, but x1 is nothing but c, so this is t, c plus c, you can take c outside, so t plus identity matrix into c. Again put k is equal to t here, 2 here, so we get x3 is equal to tx2 plus c, but x2 we have already evaluated like this, substitute it here, so t into x2, x2 is this quantity, again you have c here, so take c common, so t into t plus iota plus I c, that means t into t square, t into identity matrix t plus I c. So ultimately after k plus 1th iteration we have xk plus 1 is equal to tk plus tk minus 1 plus and so on plus t plus I into c. That means we are getting like a series when k tending to infinite. So limit k tending to infinite, xk plus 1 is nothing but limit k tending to infinite, the right hand part. So this is nothing but basically according to the previous theorem, according to this theorem, theorem number 2, this series, this is of this form, this is of this form, this is nothing but this form, I minus A inverse. So this will become basically I minus, in place of t, in place of A, here we have t, so I minus t inverse and this c. And we know that this is possible only when this happens, and this means this should happen, norm of A should be less than 1. But here you will see that what is your A according to this is your norm of T, because in place of A here in theorem number 2 we are having T, so norm of T should be less than 1. This is possible. Or norm of t means spectral norm, that means the largest eigenvalue of t should be less than 1. So rho t less than 1. So this is the proof of this theorem number 4, and we will use it in the proof of the next one. Okay, so if in case of, you can see here, in case of Jacobi method, what is your basically the matrix? Here we have I minus t inverse c, because in general this is I minus t inverse into c. Okay, so what is I minus t inverse c in Jacobi method? What is the t? If you remember what is t in Jacobi method, in Jacobi method you can see this is your Jacobi method, and this is your t minus d inverse L plus u. So substitute this t herein. So what you will get, I plus d inverse L plus u inverse, this is your t in Jacobi method, d inverse into b, because what is c? C is this d inverse b in Jacobi method. So we have substituted t as well as c both. So now from here you can take d inverse common from here, so d is inverse, when you take d inverse common, so d is multiplied herein, so d plus L plus u, and then inverse d inverse b. What is d plus L plus u? Is nothing but a. But we know that d inverse a into b inverse nothing but b inverse a inverse, so the inverse of this quantity into d inverse of this quantity, so inverse of this quantity, inverse of this means d D inverse and B. When you multiply D inverse D, we get identity matrix. So ultimately this, what is D plus L plus U is basically A inverse. This will become identity matrix and into B. So A inverse B. And we know that AX equal to B. What is A inverse B? Will be nothing but X. So X. Similarly in Gauss-Seidel method, if you will remember, what is your Gauss-Seidel method? This is your Gauss-Seidel method. Gauss-Seidel method. In Gauss-Seidel, this is your T, this is your C. Again substituted here in I minus T inverse C. So I plus this is your T and this is your C. Again you can take D plus L inverse common. So D plus L inverse. So D plus L will be multiplied in identity matrix. So D plus L. We will have U here, U, and then again inverse D plus L inverse B. So this is nothing but your A. So matrix A, this matrix multiply by this and then take in inverse. So now apply the property of matrix. So inverse of this matrix multiply by the inverse of this matrix. So D plus L inverse into D plus L. Inverse of this quantity will be nothing but हट जाएगा inverse. Multiply by this and this B. Now when you multiply these two, so we will get the identity matrix. And this is nothing but A. So A inverse B, and again A inverse B is nothing but X. So this will show that in this condition the iterative method will converge. Okay. Now in the next video we will discuss the convergence of Jacobi method and Gauss-Seidel method in detail. Okay. Thank you.